light and electrons. And what we're going to be doing is we're trying to figure out what's actually going on with light. Now, before we get started, please make sure you've got your notes, you've got something to write with, and then you are actually going to need a calculator for today because we've got some light calculations that we're going to do. Okay, so let's go ahead and get started with lights and electrons. So how does light happen? What is light, first of all? Well, light is photons, and photons are going to be typically a visual energy, a visible energy. Okay, so I know that light is a visible energy, right? It's something that I can see. How do I know that? Well, when I turn on the light, all of a sudden I can see the room, right? So light is a visible energy. Okay, so for our light, where does it come from? What happens? What is causing light to occur? Well, let's talk about when you turn on or off a light in your house. Okay, so I walk into my bedroom, and I flip on the light switch. What happens? Well, the light turns on, right? The light turns on. But why does the light turn on? What is the actual light? Where's it coming from? And a lot of times students will say, okay, well, it's coming from the heat that's inside the bulb, right? Because heat makes light. Well, not necessarily, right? Because if I'm talking about something like an LED, they don't get hot. So then what's actually going on? How does that light get produced? So it all comes down to electrons. Okay, well, you're like, okay, well, electrons, sure, but why? Okay, so what actually happens is electrons have two states that they exist. They exist in the ground state. Okay, well, what do you think that means? The ground state. Well, the ground state means that it's going to be sitting where it should be. It's sitting on the ground, right? Sitting on the energy level that it's supposed to be. So if I were to take this, and let's say I've got an atom here, and I've got 1, 2, 3, 4, 5, 6, 7, and 8 electrons, and then there's 2 right there on that first energy level. So they're all sitting on their quote-unquote ground state. Okay. Now, let's say I add some energy to them. Okay, well, what happens when you get a lot of energy? Well, a lot of times you're getting excited about something, right? Well, the other state that electrons have is the excited state. Okay, and what that means is they're going to actually jump up and down. All right, and so these electrons will actually jump to a higher energy level. Okay, well, you're like, okay, well, they're excited now, so they're jumping up and they're all of a sudden light. No, not yet, right? We haven't made light yet. So how does light happen? Okay, well, basically what's happening is those electrons have gathered in that energy, right? So they gather it in and they jump up to another energy level. Okay, well, eventually what's going to happen? Eventually, just like when you jump up, you fall down, right? Well, electrons do as well. So when they fall down, all that extra energy that they caught, that's going to be released. And it's released in the form of photons, which is light. And so, again, that's what we're seeing here. If I have the electron at its ground state, it jumps way up here, and then it eventually will fall back down. When it falls back down, we're going to release energy. Okay? And depending on how far it falls back down determines what color of light that is actually emitted. So, in this case, it falling all the way back down released red light, versus it falling just part way back down released a purple light. So we can actually get different lights by exciting different electrons and making them fall to different places. So, all right, we're good with that, right? So each line that is produced up here with that jump up and down, that's going to be where a photon of a specific energy is going to be released, right? So each line produced by emission of photons of specific energy. The colors that we have are produced by the amount of energy released in those electrons falling back down. Okay, now the energy is going to equal the difference between our ground state and the excited state. So obviously the further it falls back down, the more energy that's being released there. Okay, so why do you think different atoms will produce different or unique lines of light instead of a continuous line of light? Well, it has to do with their electrons and where the electrons are and how far they jump up, how much energy you add. If you add a lot of energy, you can get them to jump a little higher. Okay? So, what is all of this? Well, this is talking about light. So now y'all know what light is and how light happens, but in terms of what y'all have learned in the past, light falls in what we call the electromagnetic spectrum. Okay? Well, in the electromagnetic spectrum, we have electromagnetic radiation, which we call light. Now, this is our spectrum of visible light that we have. Now, if you notice, not everything here is visible because the visible section is just this very small spot right here. Okay? So everything else our eyes cannot see. But we have actually found that some animals can see deeper into the ultraviolet and some can see deeper into the infrared. So some animals can see lights that we cannot see. So what does all of this say? Well, all of this says that we've got energy in our light, right? So some wavelengths of light will go at different frequencies, right? So you're like, okay, well, what is a wavelength? Well, a wavelength is the length of a wave. It's exactly what it sounds like it is. Frequency is how often something happens. So if I'm talking about frequency, I'm talking about that repeated behavior over and over and over again. Whereas if I'm talking about wavelength, I'm talking about the distance between 2 points on a wave. Okay? All right. So that's a lot of information. So let's take a little quick pause and let's think about something y'all do know. So what are the colors of the rainbow? Okay, well, the colors of the rainbow are red, orange, yellow, green, blue, and violet. All right, one thing that I have learned in the past is that students do not recognize that indigo is not actually a color in the rainbow anymore because indigo is actually what we call a tertiary color. Okay, so first off, what do you mean by that, Mr. Oglesby? Well, let's think about our colors. So red is a primary color, right? Nothing else makes up red. Red is just red, okay? Orange is what? Orange is a combination of red and yellow, right? Okay, so red and yellow. Then I have yellow. Okay, so we know yellow is a primary color again. Then we move over and we've got green. Okay, well, green is a mixture of yellow and blue. And then I move over and I've got blue, right? And then I move a little bit further, which is also a primary color. And then I move a little bit further and I get violet. Well, if you think about it, violet really is kind of a mixture between blue and red. All right, so now I've got all my colors listed out. So where did indigo go? Well, indigo is a mixture of violet and blue. So we're talking about a mixture of colors and a primary color instead of two primary colors mixing together. So we just take indigo out, and so instead of being Roy G. Biv, it is Roy G. Bv. All right, so that is the new way of how you are supposed to be saying these. All right, now if you will notice that this actual rainbow is in the opposite direction of what you would think of with Roy G. Biv, right? Your red is here, orange, yellow, green, blue, and violet's way down there. Roy G. Biv. Okay. All right. So now we've taken a little break to do a mind check on your colors of the rainbow. So let's actually dive back into our work here with the visible spectrum of light. So when I'm talking about light, over here, I've got a short wavelength. And on this other side, I have a long wavelength. Well, what does that mean? That means that the distance between the different parts of the wave are either shorter or longer. So let's actually draw that. So I know that it's short over here, so I'm going to start in the middle, and we're going to go real short. And as we move over, we're going to get longer and longer and longer and longer until eventually we get over here to the right, where it is the longest wavelength here in our visible spectrum. Okay, so that's kind of what your eyes can actually see. We can see the really small and we can see the really long, but only in this small section of our electromagnetic spectrum. Okay? All right. So, looking at this, let's zoom into just this section over here on the left. So, I've got a short wavelength, right? So looking at our frequency, so frequency again is how often it's happening. How often do we see this wave occurring? Well, it's very, very frequently, right? It's very frequent. So in this small section, we've got 1, 2, 3 waves. 1, 2, 3 waves that have occurred. Okay, so our frequency is very high. What about our energy? Well, if you look at this, think about if you were to take a cable and wiggle it back and forth, or a slinky, if you've got one, to wiggle it back and forth. Think about if you want that slinky to move really quick and you see those waves, does that take more or less energy? Well, it takes more energy. So if you've got high frequency, you're going to have high energy. Okay. Now, if you look, that's actually the opposite of wavelength. So a short wavelength means you've got high frequency and high energy. All right, let's go over to the other side over here. So in the same distance, which is about that much, we don't even get through a single wave. So we've got a very long wavelength in this case. But what do we notice about our frequency? Our frequency doesn't happen very often, right? So our frequency is very low. So what do you think about our energy then? The energy is also going to be low. Okay, so if we've got a short wavelength, we're going to have high energy and high frequency. If we've got a long wavelength, we're going to have low frequency and low energy. All right. Now, the very last thing on this is going to be looking at our waves and actually knowing the parts of the wave. So first off, let's draw a wave. So like that. All right. So what are the parts of the wave? So the first part is if I'm going from right here, which is what we call the crest, to another crest, that's what we call our wavelength. Okay, so our wavelength is the distance from one crest to another. Okay. Down here at the bottom, this is what we call the trough. Okay, it kind of looks like a trough that you would feed an animal out of, right? The little lump that you can actually put food into or water into. Okay? The last part that you need to know is if we take our waves and we dissect them in half, the distance from the crest to the halfway point is what we call amplitude. Okay, so the distance between the crest and the halfway point is what we call our amplitude. Okay, so that is everything that y'all need to know about the EM spectrum and waves and light. So how do I actually use this in chemistry, right? Because this isn't really something that I can really apply in the real world, right? So let's actually look. Well, in chemistry, we actually sometimes have to figure out how much frequency or wavelength we've got that we're working with, all right? And so that's going to help us get an idea of the amount of energy that's there and that kind of thing. So how do we do that? Okay, so here I've got our speed of light equation, all right? We've got speed of light, which is represented by the letter C. We've got frequency, which is represented by the letter F. And we've got wavelength, which is represented by lambda. Okay, so I've got these three symbols that I'm going to use to represent those three things. Now, before we actually dive on into the work here, frequency, I did want to go over just real quick. Frequency has three different units that you could see. So frequency, you could see s to the -1. Now, if y'all know stuff about math, s to the -1 is the same as 1 over s. Okay, so kind of the same thing, but just written as in a different way. And then the other way that you could see frequency is hertz, Z. And that's probably the most common way you'll see it. Now, these are all interchangeable. So if you have hertz in a problem, you can just easily convert it over into one of the other two. Okay. Wavelength will sometimes be found in meters, and sometimes it'll be found in nanometers. Now, to remind you, nanometers, there are 1 times 10 to the 9th nanometers, and that equals 1 meter. So that's just kind of a reminder for that conversion, because nanometers is the one of the few metrics that doesn't fall into the King Henry died by drinking chocolate milk thing that we talked about earlier in the year. Okay? All right. So how do I use this equation? Well, it is a simple plug in your numbers and solve equation. All right? Now, speed of light is a constant. It is always 3.00 times 10 to the 8th meters per second. Now, since it's always a constant, you will never be asked to solve for it. Why? Because it doesn't need to be solved for. We already know it is always 3.00 times 10 to the 8th. So what we do need to do is solve for frequency or to solve for wavelength. So you do need to know how to rearrange that equation. If I'm solving for frequency, frequency is going to be the speed of light divided by wavelength. If I'm solving for wavelength, it's going to be the speed of light divided by frequency. Okay, so it is fairly simple in terms of actually figuring out how to solve it, but you do need to keep those in mind and make sure you're ready to actually manipulate that speed of light equation. Okay, so let's actually solve a problem. So my question here says, what is the frequency of green light with a wavelength of 4.90 times 10 to the negative 7th meters? So I'm solving for frequency. And I know my formula for that is the speed of light divided by wavelength. Okay, so frequency equals speed of light, which is 3.00 times 10 to the 8th meters per second, right? And then they also say that I have a wavelength of 4.90 times 10 to the negative 7th meters. Okay, well now I've got meters on top and meters on bottom, so they're basically going to cancel out. Well, if you look at this, that's going to be the unit we're looking for frequency, right? 1 over S. Okay. So I have this, and I'm going to plug it into my calculator, and what I'll find is that my frequency equals 6.12 times 10 to the 14th 1 over S. You could also, instead of 1 over S, use S to the negative 1 or hertz. Any of those will work. So this is my answer. Okay? So I actually want y'all to pause the video and actually solve this next problem. Okay? Pause your video, solve that next problem, and then we'll come back and we will work through it. All right? All right, so hopefully y'all have paused the video and worked through this problem. But what you should have found is that we have 4.75 times 10 to the negative 13th meters as our wavelength here. All right, so again, I took my wavelength formula, which is wavelength equals speed of light divided by frequency, and I plugged in my numbers here. So 3.00 times 10 to the 8th meters per second, so seconds is on the bottom, divided by 6.32 times 10 to the 20th hertz. Now remember, hertz is interchangeable with 1 over S, or S to the negative 1. I went ahead and put divided by S here because basically that's what you're doing. You're dividing by a fraction, which means you're going to cancel out those 2 seconds. Okay? All right. So then you solve for that, and you should have ended up with 4.75 times 10 to the negative 13th meters. All right? So one more time, I want y'all to pause your video and actually try this next problem, because this next problem has one extra step. So go ahead and do that. Pause your video, and we'll go ahead and go over it. Okay, so hopefully y'all paused it. Here is the work that we have. So the question was, what is the wavelength of light in nanometers, which has a frequency of 7.2 times 10 to the 14th S to the negative 1? Approximately what color would this be? Okay, so there's 2 extra things that we're doing here. One, we're having to solve for nanometers, right? So they're asking us to actually convert it into nanometers when we're done. And 2, we're actually having to predict what the color would be. So first off, I solve it like normal. So I've got my wavelength formula, wavelength equals speed of light divided by frequency, and I plugged in my numbers. And what I found was that my number was 4.17 times 10 to the negative 7. Okay, so now I've got that. So now I actually need to convert that, because that's in meters, and convert it back into nanometers. So I do that using that conversion I reminded y'all of earlier in the lesson. So 1 meter is equal to 1 times 10 to the 9th nanometers. Now I need to solve for that, and that's going to give me 417 nanometers. And then you're like, okay, Mr. Oglesby, so now I've got this, but how do I figure out what color it is? Well, we go back up here and we look at our chart. So 417 is about there-ish, which is in that violet section. So we would say our color is violet. Okay, so that would be how we get that. All right, y'all, that is everything we have for this lesson. If you've got any questions, please don't hesitate to reach out to Ms. Treese or I. Hopefully y'all have a great rest of the day. Bye, y'all.